series, Professor Marc Timme. Today, as we promised, it's going to be the start of inference of the networks. And without any further ado, I'll leave the floor for you, Professor Timme. Thank you.
There's some delay. Yeah, thank you very much. Again, I would like to try some of the food. You are, of course, welcome to whatever do, as long as everyone can attend. The last time we did the first steps towards inferring properties of network dynamical systems from recorded time series. And the basic property we try to deduce with the methods introduced last week, where the number of variables of a network, or if each unit has one variable, it's the number of units in a network. It's the number of nodes. Today we will refocus and ask for the edges. We will not ask specifically for the functional coupling, the functional form of the coupling functions, but just about the presence or absence of edges between pairs of nodes. And so in general, what we have is a dynamical system. We have n such equations for variables xi. And each of them has a rate of change given by some nonlinear function fi as a function of capital of vector x. Okay, so this is just a vector. This boldface x is a vector x1, x2, xn transpose. And in general, f is nonlinear, and also f is not known. So again, our setting is that we record now not a few, but all time series of all the xi's, and we want to infer properties of f. And the question is, what are the appropriate properties to reflect the coupling topology of the system? Then we'll learn how to, for nonlinear systems, how to derive a set of linear systems of constraint equations given the data, like given the things we can observe from the system. Can we write it down as a system of linear equations where the unknowns are some coefficients c, which is in general a matrix? And it will turn out, and I'll explain why, this is not a sparse problem in general, like not some links are present, some are not, but mathematically is more involved. It's a block sparse problem. So blocks of entries of this C matrix are non-zero, and then blocks are zero. And I'll explain why that is and how we can find such a solution roughly. And there are like standard methods, and ours is related, but not exactly the same as existing standard method. And we develop a suitable group sparse algorithm, which is greedy. So it tries to find solutions layer by layer, or unit by unit, and just keeps the best possible unit in memory first, and then checks for the best pair of possible units connecting to a given node I, assuming that the first we found is correct. So first, let us go to a very, very basic example. Here you see a network of 3 variables, and they have some local dynamics. x1 dot is h1 of x1 plus g13, like the coupling from 3 to 1, as a function of both variables x3 and x1. The same for 2. So here, if you look at variable 1 here, there should be an error here towards 1. So there's an input from 3 to 1, and the coupling function may depend on both variables. There's a second coupling function which depends on 2 and 1, which is like the input 2. And there's a third one which formally looks the same, but it's not if you take care. Like if you write it down mathematically, you would on first glance assume, okay, these have all the same form, so what should be different with unit number 3 or variable number 3? And if you closely watch, then this G12 does not depend on the variable it influences, does not depend on 3. So this is an actual 3-point interaction in the sense that node 1 jointly with 2 somehow typically nonlinearly influence node 3. And that's symbolized here by this T-shaped arrow. And it might also, some people just circle the group of involved variables. So 1, 2, and 3. The 3 is implicit here because this one appears in the rate of change of variable x3. So that's one way of writing this very basic dynamical system. And again, our assumption is that we have no idea of what exactly H1 is or what these functions are, okay? From graph theory, we know what is called an incidence matrix. An incidence matrix codes for the input nodes for each given node in a given row. For example, row 1 has here a 1, then a 0, and a 1, which means that it receives input. The right-hand side is non-zero as a function of x1. It does not receive input from x2. There's no x2 appearing on the right-hand side, and there's something appearing which includes x3, which is this 1 here. In graph theory, that is just a connectivity. So this maps the dynamical equations to some kind of graph theoretical connectivity. Here in the second line, it's the influence onto variable x2 given by variable x1 and x2. x1 here, x2 here, and there. There's no influence of variable 3 onto x2, which you also see in the graphical representation here. And the third, and that's why this is different, is a 3-point interaction where variable 3 is influenced by 3, 1, and 2. So all entries are 1. Now we define something which we can use intrinsically within the differential equation, and we call that an explicit dependency matrix. This has actually been invented by José Casadiego, who's now working in Spain. And we write the entire right-hand side, xi dot, as some unknown function fi of a matrix lambda, which is a diagonal matrix, multiplied by state vector x of the entire system. And this diagonal matrix has the following properties. So I is the index for the goal variable, the variable it changes. And the diagonal indexes are j, here, jj. And it's 1 if and only if the right-hand side does explicitly depend on xj. So in other words, if there's a variable 3 in there, then lambda 1, upper 1, lower index 3, 3 would be 1 because there's a 3. And equally lambda 1, 1, 1, 1, 1, 1 would be 1 because there's 1. And otherwise it's 0, okay? So it just tells you which of the variables are here. In other words, it has these guys, these rows on their diagonal. And this maps this graph theoretical incidence matrix to dynamical system setting for ordinary differential equations. So we rewrite this one as that one, and actually fi is the same function as capital Fi, with the exception that we explicitly put some things to 0 here. Yeah? Here, the input to a non-influencing variable is mapped to 0 within this one, and it's not explicitly 0 here. So we write like that. So now we did nothing so far, right? We replaced unknown functions by other unknown functions, and we rephrased the existence of variables by a linear multiplicative factor here, which is a matrix. So the former incidence matrix rows become the diagonals of the explicit dependency matrix. Here is 1, 0, 1 as before, 1, 1, 0, and 1, 1, 1. It has this lambda I, the explicit dependency matrix, has a number of useful features for systems of differential equations. It does multiply the system state x on the right-hand side. It explicitly appears exactly once, like it's once here, and that's it. There's no higher order whatsoever so far. Like that, we just put it in here and all is fine. And it's directly related to the graph theoretical notion of incidence. The work in which this was introduced is first authored by Jose Casallego and appeared in 2017. We now ask, what is the structure of space? Like, what space are we talking about? Typically, we talk about state space, which is a collection of all variables describing the system state. And now we take into account one more variable. So we take all the xi's, and then we take the xi dot. Like for a specific I, we take the rate of change of that as another observable. And for example, for rapidly sampled trajectories, you can estimate the rate of change by just computing the quotient and dividing by the time interval, as usual in calculus. So then you can plot a surface on top of state space and say, at which point on state space does my rate of change, like what is the rate of change at which point in state space? And this is given by fi of lambda ix. And the tangent vector is given by the gradient of that function. And so obviously if it doesn't change in one direction, like for example, if xi dot does not change into the direction of xj, then so there's no gradient or no directional derivative, zero directional derivative in this direction. That means that the function fi is constant as a function of xj, and this means it does not depend on xj. So in other words, if one variable xj does not influence the rate of change of a node I, it doesn't appear on the right-hand side, it doesn't change this f, and thus we have a relation between the topology of the interaction graph and the differential equation given here. With the main point here still that fi is not known. We don't know it. We want to find out in which direction does it not change, which are those variables where the influence is 0 on xi. You can also reverse the questions, ask in which direction does it change, and these are the variables directly influencing the rate of change of xi. So Jose calls this dynamic space because it's like the state space plus one variable. And this is pretty useful because later we'll generalize that to a notion which is similar, but is not, it comes from discrete events spaces. And we can still use the same idea that there's some function which depends on state space, and you define what state space is, the xi's and xj's, and there's some function and it changes or it does not change as a function of some of the variables. Now, the action of the explicit dependency matrix, if you do different order expansions, we'll consider now. Order expansions, by which I mean the number of variables simultaneously appearing in a non-trivial way in some functions. Okay, so first order would be there's one. You could imagine there's a constant, but then the next thing is there's one variable appearing here, and there's a sum of these guys. So if I expand this function, what I automatically get in terms of simple, I just represent fi as a sum of these lambda I jj's. They tell me whether this guy is influencing z at all. And this function gij is telling me how xj influences xi, if it's acting alone. There could be additional terms, for example, xj co-acting with xs, some other variable. And there's again, there are two factors now of the diagonal element of the explicit dependency matrix. One is lambda I jj, and one is lambda I ss. If one or both of them are zero, then the total influence of the pair xj and xs onto xi is zero, right? If there's no influence by construction, then there's no influence of xj or xs onto xi. These both are zero, and it just essentially doesn't. This means that they don't appear. The interesting thing, and you can go on to higher orders, right? So third order, whatever. The interesting thing now is that because you can write like that, the lambda I jj appears in every order as a total prefactor. And this is, sorry, it's not written here. These are sums over j every time. So once a variable, say x5, is not in the right-hand side, is something like that, okay. x5 is not in here, then lambda I 5 would be 0. And then all of these guys would be 0, right? Need to be 0. So simultaneously, they kill possible linear coefficients. So first of all, we made this, so these guys appear linearly. In a system of equation. We don't have a system of equation yet. We can estimate that from a time series, estimate from time series, okay, by approximating the differential quotient. But we have, so far, we have just got more involved because here's a nonlinear unknown function f, and we just replace that by sums over many unknown functions, g, okay? But the most important thing that explicit dependency matrix entries multiply each dependency in each order, okay? So is one thing 0, it's 0 everywhere. If it's non-zero, it's non-zero everywhere. And it appears as linear coefficients in the restricting equations. The problem is we don't have yet restricting equations because we have now still unknown functions, right? These are unknown. Unknown. Other questions or comments up to here?
Are you okay, guys, with the transformation from the incidence to this lambda? No questions?
So just to clarify, so this would mean that if it's independent of, let's say, x1, it cannot depend linearly on x1 at all. If there is a dependence on x1 and x2, then it should depend linearly on just x1 and just x2.
Linearly or not, but the point is the coefficients which tell you whether or not there is some dependence, they appear as linear prefactors, right? They appear just as prefactors. They don't appear as in a nonlinear function. They just multiply that function. The function is still unknown. I'll clarify that in the next step. But these guys appear as linear prefactors, and you want to find out whether these are. The question is, right, to find out what the connectivity is. So which of these are zero and which of these are non-zero. And it's much simpler to find out if it's in a, not like here, in a nonlinear function, but appearing linearly in a system of equations. Maybe it becomes more clear if I go to the next slide, because there I will resolve these unknown functions. So now
I cannot, so if I have, say, like G of 1, 2, then I should have also G1 and G2. That was my question. So necessarily, if I have G1, 2 being non-zero because the prefactors are non-zero, like subscript 1, 2, then I'll have necessarily G1, 2 and G2. Yeah. So if I have this factor, that means that lambda of 1, 1 and lambda of 2, 2 are non-zero. So I should have separately also G sub 1 and G sub 2, right?
Yeah, so we outsource the problem of whether it's influencing or not to the coefficients. Whether this one, I mean, if in order to not have this influencing, you need to have a constant zero function, which is a bit boring. So we outsource the problem of whether there's an influence of a joint influence from 1 to 2 to the product of these two coefficients. Okay. So if there's no influence from 1 and 2 jointly, then the product needs to be 0.
So if I may, one other way of casting this, if you have a lambda I of 1, 1 and a lambda I of 2, 2 non-zero, then the term appears.
Then the term appears, and the only way you could still make it 0 is if you put in the identical 0 function here, right? But that is, we ignore that part. Yeah. So what we now do is we expand these functions, these unknown functions. We do another set of expansion. Each of these will be expanded now in terms of basis functions. And these basis functions are called, we call them H, okay? These are just sums over basis functions. So this one was the previous G J I of xj, okay? This is G. And we just expand that in terms of basis function. In a simple form, you can think of what are good basis functions. Well, you all know Taylor expansion, I assume. So its powers HJP would be just xj to the power of p, for example. It could also be a sine function of p times xj, or any other basis you want to address. And of course, if you have a periodic problem, you might want to choose sine functions. If you have a non-periodic one and it smoothly changes from 0, maybe you want to, or from some base value, maybe you want to take polynomials near 0, so you take Taylor. But there are other options of changing basis function. You can take any set of special functions your favorite with, and later I will discuss that it will actually not depend on the details of what you do, but it will depend on a meta factor, like on a rough classification of which types of functions you include. Here, now you have something even worse, right? You have to count through many of them. So this is now G J S I of xj and xs. This is this block, and here is this even longer thing. So the main point is you get additional sums into your game, but the sums are just weights, again, linearly weighted. So these guys are appearing linearly. And so the product is still a linear number, like a linearly appearing coefficient. So the product of these guys is all blue boxes show linear coefficients multiplying some functions, which you know, okay? Basis functions are known. Basis functions are known. If you know them, for example, if this is xj to the power of p, you can substitute values into it. So once you record a time series and you know xj is this at time 5, you take the power p and then you now know xj of time 5 to the power of 5, and which is just some number to the power of p, which is just some number which is appearing here. So these are numbers. Everything here are numbers once you put in your time series recordings. Here are numbers. So in total, what you get is this. You get a linear equation. This is a collection of these derivatives. This is the collection of coefficients, and this is a collection of basis function entries. Okay, you get a matrix equation for the entire system of all xi's. You get a matrix equation with unknown coefficients, but known rate of changes and known evaluated basis functions. And now your problem is pretty simple. You want to understand which of the entries of C, as C is not only this, right? C is the entire blue block. Which of the entries of C are 0 and which are not? And you can think of, okay, maybe it's involved, but that's coming next. So it shows, because of the structure, that if lambda I jj for some fixed j is 0, then all of these guys for the same j will also be 0, right? So either you have all of them typically non-zero, like a block of non-zero existing entries in C, or you have a block of zeros. Okay, there's nothing. So these are all zeros, and these are not zeros. So you understand that once there is a non-zero entry, you probably get many of them, because you would get them in all of the orders if you correctly assemble them. And once there is a 0 entry, you get a lot of zeros because they appear in all the orders you take into account. And now, obviously, who knows Arnie?
As in Arnold Schwarzenegger.
Yeah, this guy, exactly. So Arnie is the algorithm for revealing network interactions, obviously. And what Arnie does, he shoots down individual units, okay? Well, for political correctness, we didn't show the other part of the weapon, but so he shoots it down, and we'll do the same, one by one. So you have your equations, and the first thing, like your restricting equation, the first thing you do is you assume that there's only one, so you have a node I, that's your node I, and there's only one node which is influencing node I, and this is the red one. Out of all the other ones, yeah, there are all other nodes in the network, and you ask which one, if I only had one coupling, which one is explaining my data best? In other words, which is minimizing the difference, the norm of the difference function here. You take your derivative, and then you take your derivative, your actual derivative, and then you take your reconstructed derivative, assuming you have only one node influencing node I. And you remember that, and it turns out it's the red one, okay? Second, you keep this red one, And you remember that is whatever, node number red, okay? You put it in your box. Then you project out the contribution of that. And in the subspace remaining, you try the same thing again with the best node, which helps explaining the remaining difference. And here it turns out to be, okay, the green one. So you keep the green and you say, okay, the red and the green is now my new best set. It's here. And then you again project out the contribution by this pair, like by first and the second, and you ask which of the remaining ones is best explaining the remaining difference. And then it turns out, okay, that's the blue one. And then you say, maybe there's a blue connection here. And you get to that one. And at some point, you say that there's a remainder, which is given a basis, it's some remainder of the difference of the reconstructed x dot and the actual x dot. So this is the reconstructed and this is the actual one. This is the actual one, that's the reconstructed one. And then you stop, like you stop after your error signal is dropping below some threshold, okay? Of course, the threshold is not trivial to fix in reality because, well, it depends on everything. It depends on the problem, on the resolution of your time series, on the number of data points you put in, on the nonlinearities in your system, all of which a priori is unknown if you don't know the problem. So it's a bit of not completely trivial, but we found a way which often works. And analyzing how the error drops with the number of elements L taken into account. Okay, L is like the number of nodes you take into account. So L1 here, 1, 2 here, 3 there. At some point, you stop, and the question is, what is the appropriate value to stop? So now, on purpose, we take something which had like weird dynamics, but it's still single variables. And this is a modification of the Kawimoto model, which has shift here and a bias. And also it has double the frequency here. And there's some noise on top. And we pick a random network of 30 nodes and 15 connectivity 15. So random regular network. Each guy has 15 inputs to be able to reconstruct, to see where 15 lies on our error measure. And the error drops. And these are different realizations. The error drops, and at some point it levels off. There's this L-shaped, like roughly like this, okay? L-shaped diagram of the error function, the remainder function, and the number of the number when it starts not dropping fast enough, we take as one above the predictor. So this one would be 15, okay? So here we actually predict 15 and we get 15. So we find the best 15 and we see that the error drops more slowly after you have identified 15. And that's, I have no mathematical proof, but we have observed that across different systems and settings, not always, but in a lot of cases. Now we can ask...
Mark, do you mind going back to the slide of projection? I think looking at the faces, they just needed to spend a little bit longer time with the slide, so, yeah, so it gets digested.
It's more, yes, it's more reasonable if you just first look at this. You first ask, I shouldn't do it in blue because it's actually red. You first ask, I have my equation. I had my original equation, y equals cd. Y is the rate of change. So this was something like x dot. These are the coefficients you're looking for. And this is encoding how much, who is interacting with whom, like what order and what inference. So, you do now an approximation where you say, I want to find that right-hand side D, which has only one node influencing node I. So first of all, you fix I, okay? You take only one of the lines here. Actually, it's not, it's a matrix because there is the index I, which goes from 1 to n, and then there's a time index, okay? You have a time series, which I somehow didn't explicate here. You have a time sequence, and so even for one I, you have a vector. And you try to find the one node which best describes my left-hand side, and you compare it to the actual left-hand side, and compute the error, and if the error is the smallest error is the one you take, so you collect the red node here. Once you have done that, you ask in the projected space, what is my remaining, so you have a new, or you can also formulate it more simply. Forget about projection. Now you fix the red node, and now you ask, given the red node, which other node combined with the red one does explain my x dot value best. Then you pick that one, and that turns out to be the green one, and collect and fix the red and the green. And then you go ahead like that until at some point your error is small enough, smaller than some threshold, and then you stop. In reality, so this normally you would actually stop. Or what you can do is what we did here is we just continued without breaking it, right? We just continued, looked and watched properties of how the error drops. And the error drops like an L shape roughly. And after you have collected the correct amount of input nodes, correct number of input nodes, the error drops more slowly. So what we find is we assume that this was the correct number, and which it is here. It's not always the case, and there's no like guarantee, but the method here is you can see it from the data. There's no information about what exactly did I put in and get out. We just do it, and then we get a hint from the data.
How would we know the appropriate choice of basis onto which to project?
Good question. Next, transparency. Thank you for helping me going further. So now we have chosen different types of trajectory, different types of basis functions. And you can compute an AOC score. That's the area under receiver operating characteristic curve, which I won't explain, but roughly speaking, if that is of the order of 1, you're good. Like the closer it is to 1, the better you are. And if it's about 0.5, you're essentially guessing whether a link is present or not. Like you are the same, as good as guessing. And now you do evaluate your scheme as a function of basis function. And there are 5 different ones shown here. And you can see, well, this is like powers of xj. This is powers of differences of xj and xi. This is products of differences. This is a sine and cosine of multiples of xj. And this is sine and cosine of multiples of differences of xj. What you see in the original one, that you have something like that. You have something like E, okay? This is like the correct one. And the other ones are wrong. But what you find is a pretty good approximation for B, C, and E, like this, and this, but not for D and A. Why is it? If you look carefully at which basis functions we took here, these are only single variable basis functions, but the functions we actually have in our problem are 2 variable functions. So these have coupled influences. Okay? So you need to take, so it's important it's not important to take the specific basis function, which would be E here. But it is important to select this correct type of basis function, meaning that the number of joint variables which influence the rate of change of I is the right type. This is correct here, it's correct here, and it's correct here. So here's one variable, two variables, one variable, two variables. So all these three are good. Although only the E choice is the actual one. So again, only the type of function, not the function itself, is relevant for successful reconstruction. And that's a pretty general statement. Well, we probably can't prove it, but it's we have some intuition of why that is. I mean, on there's a bidirectional statement. The one direction is simple. If you don't get sufficiently many variables, then you can't faithfully describe the right-hand side, so the rate of change of a variable, which is not surprising then that you don't reconstruct it well. If you could argue that you take into account more variables, what happens? Like if you take 3, and then it will depend on how exactly the 3 appear. Like if there's another parameter by which you effectively can put one of the 3 to 0 or silence it, essentially depending on how your basis functions. So message here is that the type of basis function is important. The exact basis function is not important. So and how you would practically do it is you start with simple ones. You start with single variable ones. And if they don't suffice, you add other ones. You can still you can also, for example, use a combination of A and B, and it would just silence these coefficients to 0 and have these coefficients non-zero, essentially. Of course, they're all numerically non-zero, but the prefactors of basis functions for case B would be much larger than those for A. Okay? Does it answer your question how to choose?
Yeah, kind of, but it also raises another question. Like when we have all these like B, C, and E that are like equally likely to be the true ones, how can we distinguish what the actual one is? Because we know the model, so we know one is more correct than the others.
Yes.
So where does this come in?
Yes, you can. So in general, you can. So the scheme here is not meant to do that. Okay. First of all, we only ask where is the connection between I and J. Yes or no? Is there some influence from J to I? Yes or no? But if you ask a more advanced question or more detailed question, which kind of model can you actually find the model, right? You want to find the right-hand side. Then you have to be more careful and also consider, for example, how many orders you take into account. It's not a trivial manner, and it's about the same question as asking, given a basis function I want to approximate any function with, how many orders do I need? And it might depend on the basis function. For example, if you want to approximate whatever third order polynomials by monomials, you need 4 terms, right? 0th order to third order term, and then you're done. If you do this, try to approximate the same with Fourier, in a Fourier basis, you need many more terms to get faithfully close to a given polynomial. So it will depend on details.
Marc, also one question related to the search algorithm for the nodes that somewhat minimize the distance. So it's an iterative scheme and it's combinatorially expensive, right?
No.
So it's no?
In general, yes. So if you want all combinations to be tested, yes. But what we do here is we took a greedy approach. We fix one, and then we go to the next, and then we go to the next. So it's in general, if you just want to check all combinations, like you say you have 15 guys, and you want to check all combinations of 15 units out of 30, good luck, right? That's combinatorial. You are not going to succeed. And that's why Jose came up with a greedy scheme, which, well, it does work.
Yeah, that's fair. Just another follow-up on this. So this is now valid for a differential equation. Would this scheme still work for maps?
Very good question. Probably yes. Let me go to the. So I have a partial answer. Don't have a full answer because we didn't fully investigate it. I would think that if we generalize that to maps, it would work similarly. but it depends on how your how smooth your map is and how you jump around in your state space a bit, I guess. Because so far everything depends on the. Remember, we had this dynamic space, and the question is whether along certain direction the gradient is 0. But to be able to compute something like the gradient, or to estimate whether it's not changing, you need well, to estimate something like derivative. If you can't do that, because your state space points are far apart, then, well, you're either lucky and it's constant and you see it immediately, or you are making a guess, essentially. But let me go to the second part of today's talk, where I show you an example for neural networks where you only see the spikes, we only see the event times, and you can still reconstruct by the same idea, basically. And that's why I guess it would also work for maps, at least in principle. Before I go there, I just show you some examples. Actually, I don't show you, I just show you the differential equations. There are now 10 different differential equations. As you can see, they are nonlinear, involving these different variables MP, P0, P1, P2, MT, T0, T1, T2, C, and Cn. So that's a model for the circadian clock of Drosophila, and it has it has 10 units, 10 variables, and nonlinear coupling, and well, that's a performance. You can try that again against other methods like standard correlation-based methods or something like that, transfer entropy and Pearson correlation. So it just says that if you take into account more, this is like the number of experiments, or number of experiments, or time points, depending on how you interpret your data. And well, if you are sufficiently large, the final, well, so the actual prediction quality is much better. Remember that at 0.5, which is here, is guessing, so you're like, I don't know, 30% improved by that method compared to only checking correlation, which is like all these three measures are actually linear measures. I mean, correlation and also transfer entropy is a nonlinear measure, but
sorry.
Yes.
I have a question. In this approach, we do not obtain a strength of interaction between the agents in the network, and only whether or not there is a link, and no weighted incidence matrix.
Yes, but you could try to generalize it in the same way we could try to generalize it to get the function out, or to get a good proxy for the function. Yeah, but so far I presented nothing about weights. Yeah, just identity.
Okay, and so in this comparison, you were comparing whether or not any of these methods just found the link.
Yeah, of course, the question is how do you find the link? And then you have to put a threshold, and the threshold is, can put it one or the other way in a systematic way. Yes, and the best choice threshold was this result.
Okay, thank you.
At least for a correlation, I know. Yeah. This is another example. Now only 7 units, but first, the strongly nonlinear coupling, and second, there are pairwise interactions, and there are also 3-point interactions involved, together with 2 points. So it's a real, well, it's a model of a real system, equilibristic oscillator in yeast, and well, that's the result. It looks roughly similar. Here you also see the strength of combining second and third order in the same, treating second and third order interaction in the same footing, because by constructing correlation can't do that, right? Like correlation is just a pairwise measure. Oh, and higher order correlation would be hard because you need to compute like 3-dimensional point clouds. Not impossible, but yeah, not so simple. And then we can try other things, like, for example, putting noise or putting recording only from some of the units. And of course, if you don't observe some of the units, hidden units here, the red ones, we wouldn't expect that you find the links between hidden units or the links between hidden and existing units, but we would hope that we get links between the recorded units, and well, you do get them here. Okay. Yeah. Again, benchmarking against other methods. So, summary of the second part of the second lecture. Well, today I am aware it's the third time. Is how to find network size from nodes we had last week. Network dynamics has been viewed as an inverse problem. So using the fact that changing topology or changing the structure in general, for example, the size, does change the dynamics. Also, if you only record from some of the units, we use that as a starting point, and we suitably arranged all the time series data we have in the detection matrix, exploited a rank inequality by sequentially increasing the number of experiments you take into account in evaluating the rank, and use this saturation property of the rank problem. Open challenges there are how can we robustly detect ranks for example, noisy data, for large matrices. But that's, well, it's a hard problem, but it's essentially a numerical linear algebra problem, which no one has solved so far. How many perceived nodes do we need? And I've shown you that in general, mathematically, it should be possible from one single node for arbitrarily large networks, which is a bit surprising, but on first glance, but it's also not surprising if you think about it, because the one node, if it's influenced by all the other variables, it reflects the full dimensionality of state space trajectories, so it should be possible. One way of treating multi-dimensional units, like if you have per node, you have several units, is disentangling them and writing down a formal network between the variables and then use the same approach. But there are also other ways, as I've shown, to ignore some of the variables and make progress there. And an outstanding problem where actually Jose and others are working on is now to combine time series data from different state space regions. So far, what I presented last week, we considered the neighborhood of either stable fixed point or the neighborhood of any other given one point in state space. And a typical situation is that you're not only lingering near one point. So most of your data will be at several typical points. And the question is, can you combine it, and does it improve your method? Can you actually reconstruct from different state space regions where you cannot from any individual one given a set of data? That's a problem. Jose has presented progress last year only, and well, it looks promising, but it's not done yet. Second part, we introduced this explicit dependency matrix, and it uniquely multiplies the system state exactly once, and it translates the problem where the problem is in a nonlinearity of my right-hand side f. Translate that to linear coefficients. That's the main point. So we get, although we have a fully nonlinear problem, we translate that to a problem with linear coefficients. And then I don't want to overemphasize the algorithm, but it's a neat contribution which actually does operate okay, and you have a purely data-driven indicator of whether you are good or not, whether you have to take into account more nodes or whether you don't have to. If your leveling off of the error function is getting smaller. And next I'll show you this one. session not shown because it's not shown yet, but it will be shown in a few minutes. We exploit the exact same space. So before we had this dynamic space, we have xi dot here, and the variables xj and xi, like all the variables arranged here, and we had this fi of x vector. And now we use the same idea with spike patterns. So we have neurons emitting pulses, and we only assume that we know the pulse times of all the neurons. Can we still do that? Although these pulse times are discrete, their dependency on suitably chosen new state variables are actually continuous. And so, yes, you can make progress there. And I have not shown, you today as well, or so far, is from the statistics of time series. I'll also go to that one, but I think I will save this one to next week. Whereas that one I'll present now if you want. How is your brain activity doing?
I think it's plenty of spikes, so like
It's
but
still
like
good, or
yeah, it's still good.
or stressful? Okay, then give me a few minutes because I need to switch the slides set.
Do we break for a couple minutes? They can grab coffee or
Yeah, go ahead. Please break. Maybe we all break for next meet at 5 past. Okay.
Okay, good.
Okay. Yeah, welcome back.
Yeah, just okay. One small question before we begin. We had previously talked about inferring the size of the network, and then we talked about inferring the links. But we said that inferring the links cannot be done for nodes that we don't observe. So is there any way to relate these two methods, or to infer links with nodes that we don't observe, or is it something you're working on? Is it within the realm of possibility?
I'm not sure how far that could work. In principle, it could work. Like if you have lots of very high precision data, you should be able to identify first how many dimensions you have, like how many nodes are actually missing, and then give them names, yeah, give them labels, and then ask which of those influence which other. And in particular, it should be less hard. Like I'm not saying it works, but it should be less hard the closer those nodes are. Like so imagine you have a couple of nodes which are all directly connected to those nodes you observe. These should be much easier to, or less hard to infer the existence and their coupling to existing nodes and possibly among them if they are directly coupled to the observed ones. Because other literature in the forward, studying forward problem, like studying dependence or properties of given systems, have found that, for example, if you drive a chain of oscillators with the periodic signal and you ask what happens to the response amplitude, that drops exponentially with distance from the driving from the driven nodes. So this means that distant nodes, I would expect generally, are probably exponentially suppressed. So finding them will be exponentially harder than finding close non-observed nodes. But whether or how exactly that could be done, I'm not sure. But well, if you're interested, it's certainly worth exploring, because there's no mathematics, no obstacle I know of which principally forbids that you can find it.
Okay, thank you.
I have another question. Regarding the choice of the time series that we want to pick for our system, sometimes we can pick among many different time series that would represent, so for the same node, there are many time series that we can pick. Are there any assumptions that you make regarding the nature of the time series, or any would work?
So for the first part, for finding the dimensionality of state space, you need to have need to have pieces of time series which are near any fixed given point in state space. And the best option you can do is take all of them into account, one by one, and like add more and more until you have explored all. For the second method of finding the topology, you don't need that. You can take state space trajectories, and here there as well, it should be well, if they are local, it helps, and if they are non-local, you are hopefully, I mean, this is what I mentioned last, hopefully we can make progress to combine different locations. Essentially what you evaluate is something, derivatives at different points in dynamic space. And which to use, in general, it's hard to say. One thing we can say about trajectories is so for example, assume you have coupled identical oscillators, and they're coupled strongly, so they're all fully synchronized. They all have the exact same dynamics. So obviously, when all oscillators have the same dynamics, you can't say anything, right? You don't see any relation. So one message here is that you want diversity, you want non-identical dynamics, and this means it translates to preferring transients or far from asymptotics, like of course you don't want to be on an invariant set, or sorry, on a periodic orbit, for example, but you also don't want to be very close because it makes it numerically hard to distinguish. So you want genuine transients towards something or away from something, which give you, well, roughly speaking, it's not mathematically correct, but roughly speaking, linearly independent contributions. You want vectors which look like trajectories which look different.
So
you prefer earlier parts of a transient compared to later parts of a transient.
So practically, you're saying non-correlated or not highly correlated time series representing the states of the nodes would be best.
That's good. Yeah, that's a good way of putting it. Although here again, because it's all nonlinear, correlation itself is not giving a final word, but yes, it's like about nonlinear correlation. You don't want identically looking time series.
Also, how would the method work for time series that are stochastic? And
you just suggested a nice research project.
Okay.
It depends a lot on everything, on the boundary conditions, on what kind of stochastic process, on possible nonlinearities in your system. And if you fix everything of that, then maybe you can provide partial answers, but in general, there's no theory.
All right, thank you.
You're welcome. Okay, so my mouse here. One basic idea was that there's some function here which depends on the state variables, which actually are the original variables of my system, and then the rate of change, because I assume it's driven by the time evolution rule is a different ordinary differential equation. So there's some function fi of x which defines the rate of change of xi as a function of point in state space you locate, the system's locate. And the idea was the system does not depend on a variable xj if along that direction it doesn't change, like if it's constant like this, right? If it were constant in this direction, it doesn't change. If it's not constant like here, it does depend on xj. Now, these are the original natural variables of a system, which are in our model systems, the mathematical variables. Typically, you don't observe or not typically, but frequently, you do not observe the immediate variables of a system, but you observe something else. And so we had two kinds of constraints here. First was smooth trajectories. So there is, you are able to estimate time derivatives and stuff. And in part 3a, which I'll present today, we'll consider inference from event timing patterns, which are discrete patterns in space and time. And the second constraint so far was time ordered data. So you have actual time series in the sense that you have state space points associated with given times for different times. So we have a sequence of time evolution. There's some error of time and sort of labels of time. But frequently you don't get it. For example, you might get averages of times, or you might just get the time, not the collection of state space points traversed within a time series, but you don't know where the trajectory has been at which time. And so this will be part 3b, which I'll present next week, I guess. 24, what is it? 24th, is that right? Next week will then be followed by something which is not inference anymore, which is non-equilibrium responses of you drive a system and you go forward. So today, the remainder of today will be spent with part 3a, inferring from event timing patterns. So say you have physical units, something like neurons. You can also think of tweets, like events in a social communication network. But then, of course, these are strongly driven from the outside, and the outside is controlled, like there's agency involved and stuff, and everything is not modeled in this model setting I present today. But in principle, you can think of something which is not neurons and generates events. So there are physical interactions, and there are typically time series or whatever this means, but we ask for direct physical interactions, meaning that we ask for the synapses. We ask which neuron is physically connected to which other neuron. We're not asking for correlations, which is causing stuff. We are actually asking for the physics, like in the same way as it was with the differential equation. We ask what is somehow on the right-hand side, what influences directly my time evolution. We had that. The event is when we hit some subspace. So here it was a wall, but in a neuron, it is a threshold. Oh, that's not working properly. I have to go out here. Maybe that's bad. Okay, so in a neuron, neurons are also can be considered as hybrid systems in the sense that they have a smooth time evolution until something happens. And for those of you who are not familiar with nerve cells, there are many types, and one type roughly looks like that. It has a cell body, which is like the core of the cell where all the metabolism stuff is, most of the metabolism is going on. Then it has a dendritic tree or dendrite where inputs are coming in. And the inputs are electrical pulses, and they're collected and flowing down the dendritic tree here. Are collected here, and depending on this, depending on the state of the cell body, whose main variable is the membrane potential, the voltage between inside and outside of the cell might emit an action potential, so an electrical signal itself, which then propagates along an axon. It might be mulated or not, it's not important, it's just some transportation line, and then transferred to other neurons, which are like outputs. Okay. So the important thing here is there's a voltage, the voltage might cross the threshold, or some other variable might cross the threshold. And so this causes an event, and the event is just propagation and transfer of a signal to connected other neurons. And now if you measure the membrane potential, there's a smooth excursion of the voltage, and then there's a rapid change, which are these events. So and this might repeat, and how it's coded, and what you actually often can only measure from the outside is, so first of all, there's a threshold here, or seems to be a threshold, and second, you only observe the event times. So if you don't measure intracellularly, but with an electrode from the outside of the neuron, what you can record is these spikes, but you don't see the potential. You only see the excursions, the rapid things. So, and these are event times, or so-called spike trains. So you get sequences of event times. This is the thing you observe. Then in a setting of many neurons, you get different kinds of patterns. So here that's models of motor neurons, and there's a stimulus coming into the motor area of, I think, a model of a rat, which then, as you see, somehow the activity of some of the neurons goes up in the sense of there's more spikes for some of them after time zero. So this increasing activity. But the main point here is what you get is spike patterns. So you get, for each neuron, you get a collection of spike times, and there's no more information than that. And for neuron 7, you get this, for neuron 6, you get this. And so you have to live with that, and these are your data you can process. Okay. So networks of neurons are hybrid systems. They have smooth evolution, and they have event times. These are spike trains. And they have event timing patterns, which are spike patterns or collection of spike trains. Okay, this is like the spike train business is a slang word for event timing patterns of emitting electrical pulses. And I further abstracted. I consider first a network of 2 neurons, and it's a model network. And you assume that without coupling, like if you just leave the neurons alone, they would emit something maybe. If you drive them with a constant current, they would just emit the blue spike train. And now you do the same, but in addition, you couple them. Then there's this emission here, that emission, and somehow there's a coupling from neuron 2 to 1, and it accelerates the next spike. So it shifts the next spike to earlier times. So the message here is that if there's coupling, it changes how the spike patterns are emitted. Now, in general, you can't record what happens without the coupling, but we can record what happens with the coupling. So you see only the black lines, okay? So you see the recorded black times. And from those, you can compute what is called the interspike interval. That's the differences between one and the next spike, and they may be different. I mean, it's not super clear here, but this one, for example, is a bit longer than that one. So they depend on time as well, but they are discrete events, like they are variables. And then there's what we call cross spike intervals. It's the difference in timing between an event of neuron 1 and an event of neuron 2, or in general, it's just any 2 neurons, and you measure the spike time difference. And what the assumption here is for this simple, so assume you would know that it is just this system. You have a system of 2, then you would assume that somehow this delta t, the interspike interval of that neuron, is a function of the cross spike interval. And in other words, it's somehow influenced by the coupling here, right? The more coupling, the more it might change this, for example. So there's the main assumption is there's some smooth function, H1, which maps the cross spike interval into the interspike interval. In general, for many neurons, you have an interspike interval with index m, which again is like the index m is 1 here and 2 there and 3 there and so on. That's a function of the collection of all cross-spike intervals, because it could be influenced from all the other guys in principle, right? Shifts could be influenced there. And so delta Tim is some function which is a fixed but unknown function of the W vector, the cross-spike intervals, at event number m, and multiplied again by the same explicit dependency matrix. So really the assumption here is weak and strong at the same time. It's strong because now what we do, we assume that somehow we can count them, and if we increase the index here m to the next one, we can still do that here, which is not generally the case because they could be much faster or slower spiking. But assume that's not a problem. Then there's a second assumption, which is somehow also weak and strong, that there is some function. It's like a deterministic function. It tells you what the interspike interval is as a function of all the influences. Not surprising, but also not clear that it's actually true. So now we do the same thing. We just span our state space, which is the space spanned by all cross-spike intervals, and the interspike interval is the one additional direction. Okay, so again, this is in n+1 dimensional space, or n-1 plus 1, depending on whether you want this to define your own interspike interval. Anyway, that's not important, but it's a function in this space depending on the wij's. And any of this collection of spikes, like these spikes, these two and these others, give you one point in the space. And the point, because it's a deterministic function by assumption, is lying on a smooth manifold, if that's a smooth function. Now, because it's a smooth function, you can compute derivatives. That would be some offset point, which is just, for example, the center of many points you have, and compute the derivative. And then, because of this explicit dependency matrix again, you would get the differences in W with respect to the offset point, which is like point down here, right, in the state space of cross-spike intervals. And what you see again, that you can map this over, and then you get something which is measured, like this is a measured quantity, this is measured quantity, and these are measured quantities, and something which is a coefficient, which you don't know. And so you get the same kind of relation, and you can apply similar methods. We actually did more crude methods for this paper, where we find the coefficient matrix in a simpler way. And I just briefly want to sketch what's happening here. Alpha is something like the weight, and the weight can be, well, either zero-ish, like non-connections. Of course, it's not zero numerically, but it's something small, and something larger. So this is a network of 100 units with 10% connectivity and 300 events per neuron, 300 spikes per neuron. And you see that you can well distinguish the existing connections from the non-existing connections. You can also do that if you have mixed so-called inhibitory and excitatory connections. Inhibitory connections are those which delay the next spike of the influenced neuron. Excitatory ones are those which shorten the interspike interval. So that's why excitation, like the positive interaction, is with the negative changes. It shortens the interval because it's if you give a positive kick to the voltage of the postsynaptic neuron, it will spike earlier. So the interspike interval will be shorter. That's why this one is a negative value, it's a positive value. And you can, well, in this case, distinguish the signs of interactions. And the presence and absence of interactions. So that's instead of saying, okay, we can now reconstruct all neural networks, we're not saying that. We're saying that in principle, the same method does apply to systems which only have, where you only have event times as your output. So you don't need actual differential equation or the smooth, you don't need recordings of the voltages, for example. But it's really only the first step, and there are so many open problems here that, but I won't go into that. In the paper that we mentioned a few more. And I think I have one example where you can see decay of performance as a measure of irregularity of the pattern, which is, well, which over here. Is there a question?
Yes, Mark, if you had a time series, which is, let's say, sampled from a Poisson, and you're after the connectivity matrix, you can just look at it as a, let's say, binomial, that when there's a count, then that's one, that when it's zero, it's just zero, and try to infer the connectivity, and then you'd still get signs about following this approach.
I don't understand.
Yeah, so let's assume that you have nodes which have counts of, let's say, COVID counts. Okay, and then instead of looking at the actual counts, you'd say if this node has an infection, that's, you know, that's a spike, and if it doesn't, that's no spike. With this approach, you can infer the connectivity matrix, and then you can get it as a signed graph, right?
I don't get why, under which condition would you get a negative sign?
In this case, where you have excitatory and inhibitory, kind of similar, no?
Yeah,
Maybe
this I get, yes, you get a weighted graph, yes, but or a signed graph, exactly. But I don't get how you would relate it to COVID, for example.
I mean, just think of nodes as being countries. And
like who is influencing the other?
Yes,
Can you...
absolutely. Yeah, so you have counts and then daily counts per se.
So you're saying that one country is influencing another country negatively in the sense of it reduces? Yeah. How would it do that?
Maybe through policy, like you've kind of disconnected, like stopped.
Yeah, well, in principle, you could consider that. I'm not sure how well that works, because the base assumption here is that you have a constant, temporally constant function hi, right? And in policy making, nothing is constant.
Sure.
But in principle, yes. So the idea should be the same. Also, if you have many data,
I mean, split it over interval, at least when
exactly. Like if you have many data for a longer time interval at which you can assume that this interaction is roughly constant, then you could make progress by combining different pieces of approximately constant ages.
Yes, that's fair. Thank you.
But I have zero experience there. So this is just to say the closest sampling improves inference quality. So this is essentially saying about, no, there are two messages here. You can ask which point to take. Let's go back to this. So you can, the blacks are all your, like schematically, all your measurements. You can take like a random set and compare them with the blue one, or you can take only the closest few. Like if you take, how many are these? 7, 8, yeah, the 8 points, closest to 7 plus the blue, or you take the blue plus 7 other points. It just tells you that random sampling is not as good as local sampling. That's this one. Random sampling is red. That's the quality again. AUC score 50% is guessing. And it doesn't matter if everything is nice and regular, because everything is close anyway. So the randomly sampled point would be relatively close to your offset point in any case. But if you have very irregular spike patterns, you would essentially decay your predicting power to close to guessing. And that's because you try to approximate a linear function, very roughly, a linear function over a large stretch of a function where it's actually nonlinear. So you guess something stupid. If you, on the other hand, have many data and take closest only points, then you can still do that. Even you get more variation here because you have less quality data in some sense, but you still get reasonable performance even for very irregular patterns. It still comes with a lot of caveats. And here, really a lot of data go in to get this quality. So not only from one of these pictures, right? You imagine much larger data sets, but again, proof of principle, it could operate, the idea is valid, and it does translate. The idea of translating the dynamic space to these event spaces is a valid approach, and well, the exact numbers of performance depend on all kinds of details.
When you say irregular, maybe if we're looking at one-time series, these jumps could be irregular, but when they happen, they're coupled to others in the system. So are you saying that looking at one-time series, they're irregular, or in the system, they're just not coupled in that sense?
No, that irregular does not mean it's not coupled. It could mean that it is densely coupled. For example, in neuroscience theory, there's a concept of the balanced state, which assumes that there's gigantic networks and huge numbers of synapses and spikes coming into all of the neurons, which in turn creates the randomness. Like if you have lots of positive and lots of negative pulses, then more or less what your membrane potential, the voltage does, it fluctuates around, and at some point it crosses threshold. So it's more or less a random process to generate the spikes, which then leads to the irregular patterns. So irregular does not mean it's not strongly coupled or not densely coupled or anything like that.
But then why wouldn't we pick up on a link between two nodes that both follow irregular patterns, but when one spikes, the other spikes as well?
If that is true, if this is always the case, you will pick it up.
Okay.
If you have repeated action and this is consistently the case over sufficiently many data slots, you will pick it up.
All right, thanks.
Yeah, that's just saying that you can try compare it again with statistical approaches. There's, for example, a famous old approach of so-called spike-triggered averages, which compute differences compared to the spike moment of one neuron. It's not important what it is in detail, but it's a standard method in neuroscience, and well, this, like our approach, is still substantially better, but it's not, also you see it's not perfect, and that one is not super bad. It's just saying, well, for this example, it's better. So it's a big open problem. Also, what Sarah just mentioned, if you assume other models of event-based statistics. I mentioned Twitter or any social network activity in the beginning. It might be working there, but only under circumstances where you have good idea of the external influences and the agency of the people who interact. Like for example, in certain computer games where the rules are more or less deterministic. Doesn't mean that the game is deterministic, but the rules, like if this happens, then something else typically happens. If something that is the rule for all, is part of the rule for all of the actions, then you have good chances. Whereas if every user, like users of a big social network, have their own agency and depend on what they've eaten for lunch, then it's very hard to say, because you have a highly and strongly driven, externally driven system. Hard to predict. I think I would stop here and continue with that one next week. As I said, the part 3b is about the statistics of dynamics. Maybe I can teaser it a bit. So I won't tell you any of the formulas now, but so assume instead of time series, you only have like the structure in state space where things have gone, right? it's like you have states, and you see where the system has been, but you don't know when it has been where. And you do that under different circumstances and different driving signals. And then you average. For example, one average method is just finding the center of mass of all the points. If you do that, you would end up with some center of mass, and then the center of mass moves if you drive the system. And in the simplest driving signal is driving the entire system with a constant, okay, the constant vector, adding it to the right-hand side. And now what we argue is that this thing might behave similarly to a system which has a fixed point here, and you drive it with a signal. And so this idea maps the problem of having only the statistics of time series to an inference problem where you can deduce topological features under certain conditions. This work with also with Jose and with Monica she's now at Hebrew University. With that, if no more questions, thank you for today.
Thank you so much, Marc. And I guess no questions from the crowd anymore. They have a lot to digest. Yes.
Yes.
Yeah. And
there are a lot of, I mean, I really see that, and I try to emphasize, as you see, there are a lot of open-ended, open question, open ends where research is still valuable. For example, stochastic system was mentioned before. It's a big business. But there's not, I think it should be addressed by starting with simple, well-defined examples and then branching. So everything I've presented the last days was, the last lectures was essentially like that. So you go down to basic questions and then start with basic systems and show whether it works and under which condition it might.
Yeah, absolutely. And maybe for the stochastic question, Andre, maybe you can follow up with a question in written form by email. So he's here.
I'm here, yeah. Actually, I might be very slow in responding from essentially now on to next Monday. I mean, feel free to send me an email, but if I don't respond, just send another email next Tuesday because I will be traveling.
Sure,
Okay.
thank you.
Thank you so much, Marc. And looking forward for our last of the sessions is going to be scheduled on the 23rd. It's a Thursday, I guess. And that would be the last, unfortunately. But I guess would have
Happy
learned
to come
a lot
back
by then. Yeah, until probably potentially, I hope one day we'll have him on campus. Thank you so much, Marc, and enjoy the week.
Thank you, Sarah. Thank you, everyone. Enjoy the week. Yes. Bye-bye.
Bye.